Hi, this is Chris. Today, Nick and I will talk about a project that we are recently working on. As you can see, the Bayesian matrix factorization with Gibbs sampling in film rating predictions. First, we will briefly introduce the background of our project, Bayesian inference and matrix factorization. Then we will discuss the Gibbs sampling and its role in our project. Then follows our implementation details. And finally, we will end with a result discussion.
This is Nick. I'm going to talk about the introduction of our project. So let's first take a look at this rating chart. You can see that there are some blank spaces. For example, user A doesn't have a rating for movie 2. What we want to do is to predict this rating based on the existing data. Matrix factorization is one possible solution. It's a well-known robust method for collaborative filtering in machine learning. Using matrix factorization, instead of predicting n times n entries, we only need to predict n times k plus n times k entries. Here k is the dimension of the latent field and is much smaller than m and n. However, directly performing the factorization can be unrealistic and inaccurate, given that the dataset could be enormous or sparse. To make the factorization practicable, we can apply the Bayesian inference to further reduce the computation complexity and increase the model accuracy. We first consider every column of E and V as a multivariate random variable. Then we pick a prior distribution for them, the standard normal distribution in this case. Then we use the testing set to get the posterior distribution. However, when k increases, the computation complexity can still increase because the multivariate integration is intractable. There are many methods to solve this problem, and we choose to use the Markov chain and Gibbs sampling.
Well, what is Gibbs sampling? Generally speaking, Gibbs sampling is just like functional iterations. Divide a matrix into several column vectors. We sample one vector, assuming all the others are fixed, and then update it. Then we move on to sample and update the next vector. We aim to achieve a stable state by doing this repeatedly. Why should we incorporate Gibbs sampling in our project? Because first, in Bayesian inference, the property of a certain random variable is described by its invisible PDF. But we cannot directly display the PDF of a variable in a programming language. All we have is a fixed value. So sampling is needed to simulate its PDF. Plus, by fixing a lot of variables, we reduce the computational complexity a lot. Thus, Gibbs sampling would be an extraordinary choice. We use Gibbs sampling to train our model based on the formula we derive. Next, Nick will introduce our implementation details.
The posterior distribution of each column of U and V after training using Gibbs sampling can be further used to predict ratings. Using Bayesian inference, we had the following formulas. The likelihood of a rating RAB given the testing set equals to the integration of the likelihood of RAB given UA and UB VB times the posterior distribution of UA and VB. And this equals the expectation of the likelihood of RAB given UA and VB of the UV distribution. Because it's not practical to directly calculate this expectation, we need to approximate it using the sample mean. To sample the ratings, we don't need to calculate the MAP because the ratings are discrete. Instead, we only need to do hypothesis testing on every possible rating value and choose the value with the highest likelihood.
We have tested different parameters, and here is our result. The time complexity of our code is cubic, so due to computational resource constraints, we have limited testing results. From the figures, we can see that the RMSE values fall into the range of 1.15 to 1.35. If we control the variables, for example, we observe how its performance varies with the changes of k, then we find that when k increases, the error rate falls. If we look at the changes with iteration times, we can see that it tends to decrease but is unstable. So it's hard for us to determine if the Markov chain achieves balance when we adjust the iteration times. Furthermore, an initial variance of 0.5 is shown to be more unstable compared to a variance of 1. We find other implementations in a paper. Their results ranges from 0.8 to 1.1. Note that the ratings in their datasets only have 5 values ranging from 1 to 5. But we have 10 values from 0.5 to 5. This may be one reason why our RMSE is larger than theirs. Plus, our simplification in the initial settings may also lead to an increased error rate. Furthermore, further optimizations can be done to improve our implementation. And that's all for our project. Thank you.
Thank you.
Peace.